Hi, Geometry. This is Unit 3, Lesson 1, and we're on page 309 of your workbooks. And our first lesson in Lesson 3 is about scale drawings. So the page I'm using is not identical to your workbook, but everything is the same. It's just I don't have the diagram in color, and my first two sentences are written below the diagram instead of above. So let's take a look at this diagram. It says Diego took a picture of a hippo. That would be the original hippo on the left, and then edited it. Which is the distorted image, and how can you tell? So I'm looking at hippo A and hippo B, and I'm looking for the one that's distorted. And we might recognize that would be hippo A. This is the distorted image. And this is the non-distorted image. We can call this my scale drawing. It's a scaled down copy. It's reduced in size of my original hippo. So in this case, this would be my distorted and this would be my scale drawing. And we could say that the original and this smaller hippo B are similar in geometry. So the original hippo and hippo B are what we say similar. So in Unit 2, we studied congruence, which meant they were exactly the same size, exactly the same shape. In Unit 3, we're going to be studying similarity, which are when two objects are the same shape, but they are not the same size. So let's take a look at the second question. Is there anything about the picture you could measure to test whether there's been a distortion? There is. It's called the scale factor. So is one of the first things you noticed about this hippo is that it's too wide, that it seemed much wider for its height than the original? That's because if I look at the height to width ratio, and a ratio is generally a fraction, height to width ratio, they should be the same to have the same shape. And that is called the scale factor. And I'm going to talk more about that on the next page. But in order to have the same shape, we mean for them to be similar. They are not the same size, they are the same shape. And so what does it mean to be similar? So at the bottom of our page, let's write down our definition for similar. Well, our beginning definition for similar. Two polygons, or in this case, it was hippos, but two polygons, those are our triangles, our rectangles, our squares, pentagons, hexagons, are similar if one corresponding angles are congruent and two, our corresponding sides are not congruent. Our corresponding sides are in proportion. And my proportion will be my scale factor we're going to learn about on the next page. So let's turn to page 310. Again, I'm using a similar page. It's not identical, but I believe the only difference here is that your CH is more to the left and your KO is also more to the left. But that would be it. Other than that, our pages are the same. So I want to do a few notes about scale factor first. So scale factor, we use the book for a moment uses the variable R, but most textbooks, workbooks, videos use K, so I'm going to use K with you as well. So my scale factor is represented as K. When K equals 1, we call that an isometry. And in an isometry, size does not change. This would be everything we've been studying that were congruent. They were always the same exact size. Nothing changed. When my K is greater than 1, we call that an enlargement. This is when my scale factor is something bigger than 1, my size gets bigger. Hope I'm writing on top of this. Let me go ahead and get rid of my illustrative mathematics logo. There we go. Size gets bigger by the scale factor. And then if my K is in between 0 and 1, so a fraction like 1/3, 1/2, half is big, a third is big, 3/4 is big, 1/5 is big. If my K is between 0 and 1, we call that a reduction. And my size gets smaller by, and I'm going to use quotes here for the words right above, the scale factor. So let's take a look at an example that does both an enlargement and a reduction. So sketching the stretching is what it says. A dilation with center O and a positive scale factor K. Can we please change that to a K? This is a positive scale factor K. Takes a point P along a ray to another point whose distance is K times farther away. So if K is less than 1, then a new point is really closer, not farther away. So they're really talking about what I've laid out above for you. When K is greater than 1, it's going to be farther away along that same ray, and so it gets bigger. And when K is less than 1, but greater than 0, it's going to get closer to my center. It's going to be a reduction. It's going to get smaller. So let's take a look at the first one. It says dilate H. That means H is going to be moving. Using C as the center, that means C is fixed. My center does not move. And it says the scale factor is 3. So my scale factor is 3. This is greater than 1, so this is going to be enlargement. And it tells me that H is 40 millimeters from C. So for Unit 3, you are going to need a ruler or a protractor that has millimeters. So really what you want is a protractor or ruler that happens to have centimeters. So the metric system is based on tens. So for instance, this is my protractor, and this is my inches ruler across the bottom. This is my centimeter ruler. You'll notice it says mm. So these are really 1 centimeter, but that means it's 10 millimeters. 2 centimeters, it's really 20 millimeters. 3 centimeters is really 30 millimeters. My metric system is based on 10. So my millimeters is just 10 times whatever I see for my centimeters. Same thing with this ruler. One side is inches. The other side is actually centimeters. You'll see that it has mm for millimeters, and underneath it says centimeters. So 1 centimeter is really 10 millimeters. 2 centimeters is really 20 millimeters. 3 centimeters is really 30 millimeters. So if you have a problem getting either a protractor or a ruler for our class, please let me know as soon as possible via email, and I'll try to help you with that. And you will also need to be using your compass again. So also if you have a difficulty with a compass, you need to let me know as soon as possible. Okay, so here we're going to get started. So my scale factor is 3. So right now, H is 40 millimeters from C. You might be thinking in your head, well, if the distance between H and C is 40, and I'm going to make it 3 times bigger, my new distance between my center C and my H prime should be 120 millimeters. And you're right. So let's lightly draw a line, just really lightly, because this is not my answer. And then let's start measuring this off. So this is my 40 millimeters. You can see that I'm at 4 centimeters. So let's move it over and mark 4 more. So this is my 4 centimeters, which is another 40 millimeters. And then let's do it one more time at the very edge of the page. Almost went off my page. So here's another 40 millimeters. Here's another 40 millimeters. And this is my 120 millimeters total from C to my new H prime. So I've now dilated H using center C with a scale factor of 3. In other words, H prime is 3 times as far from C as H was. This is an enlargement. So 3 times the distance from C to H will equal the distance from C to H prime. C to H prime is 3 times bigger than the original. So let's take a look at a reduction. So on number 2, though, before you get started, your book and this paper has a slight mistake. The segment that they give you is not 40 millimeters. So can we fix that before we even get started? So your book, I believe, is a little different than mine, but just slide this over, put your ruler or your protractor, slide it over, and make your O here instead. And that's really my 40 millimeters. So I'm gonna be really working with this segment right here. So now we're all set. It says dilate K using O as the center. You don't have to worry about it in your books, but I'm gonna get rid of this for the video so it's not confusing anybody. Using O as the center and a scale factor of 3/4. So you guys, this 3/4 is between my 0 and 1. So it's gonna be 3/4 as far away. So it's actually gonna get closer to O. So my K is gonna come in so that K prime is 3/4 the distance from O that K is. So it's gonna get smaller, it's gonna shrink in. So let's figure out what that distance is. Let's do the same thing we did up here. Let's take my distance of 40. Let's multiply by my scale factor of 3/4. And this is really 40 over 1. 40 times 3, 120 over 4. I'm getting 30 for my answer, 30 millimeters. So that's telling me that K prime is going to be 30 millimeters from O. So let's put that on here. The easiest way to do that is actually to put my 3 on O. So this is my 3 centimeters. This is my 30 millimeters. And then where your 0 is, that's where your K prime is going to be. And that distance between K prime and O should be 30 millimeters. So the distance from O to K prime is 3/4 of the distance from O to K. So you could say in this problem that 3/4 the original, which is O to K, is equal to my O to K prime. So my 3/4 of the original is equal to my new image. And it got smaller because my scale factor was a fraction. Okay, ladies and gentlemen, let's go ahead and go to the practice problems. I'd like to talk about numbers 1, 2, and 3 with you. So let's take a look at the first one. This is on page 313 of your books. So I'm on page 313. It says polygon Q is a scaled copy of P. So that tells me that this is the original, and it tells me that this is my image. So let's look at our first question. It says the value of x is 6. So let's write that in right here, x equals 6. And it says, what's the value of y? So notice that the blue figure and the green figure are the same shape, but they are a different size. This would be a reduction. It got smaller. So this side was 6. This side will be something smaller than 6 now. Let's find out what it is. We set up a proportion, and really there's actually quite a few different proportions that you can set up. And as we get farther into this unit, you'll start to get more confident. But we're going to just write a proportion for this today. And this is going to be 2 equal ratios, or 2 equal fractions. So it's important to know your corresponding sides. So your first ratio, you've got a lot of options. I'm simply going to write my side that's 4 over my side that's 6. So both of these are in my blue figure, and it's my shorter side over my longer side. So now I go to my green figure, and I need to set up that same ratio. So I'm going to need to do my top over my side. So I'm going to set up the same ratio of 3 over y. And now I'm going to solve this proportion. So I'm going to cross multiply, and I'm going to get 4 times y, or 4y, equals 6 times 3, which is 18. Divide both sides by 4. And I'm actually going to leave my answer as a top-heavy fraction, but I am going to reduce both the 18 and the 4 by 2. 18 divided by 2 is 9. 4 divided by 2 is 2. And I'm going to leave my answer as 9/2. Could you write 4 1/2? Could you write 4.5? Sure. But the way our book does a lot of these problems is that it leaves its answer as a top-heavy fraction. So the value of y equals 9/2. There are other proportions you could write that are true for this diagram, but you are still going to get 9/2 for your y. So what's the scale factor? The scale factor is always a side from the image over a side from the original. So which side? It doesn't really matter. So in this problem, I'm going to use the 3 and the 4. So in this case, if I use my 3 on top, that's in my image, I'm going to use the matching 4. So my scale factor for this problem is 3/4. In other words, this is 3/4 the size of the original. So let's take a look at the second one. This is going to be about setting up all those true proportions. So these two figures are the same, except my figure F is smaller. Everything about it got smaller. Other than that, these two figures are what we call similar. They're the same shape, but they're not the same size. So we know that AB, this total distance is 6. We know that CD, the total distance is 3. We know that XY, the total distance is 4. And we know ZW, this distance is A. So it wants me to select all the true proportions. So let's write a couple. So when you write a proportion, you have to have the corresponding parts in the same order. So for example, I can keep everything from this figure E together. So I could use the 3 and the 6. So I could put the 3 over the 6 as one of my ratios. This is the smaller side in figure E. This is the larger side in figure E. So what should that be equal to? Well, that should be equal to then the smaller side in figure F over the larger side in figure F. So when I look at that, the smaller side in figure F is A. A and 3 are in corresponding positions. So my numerator would be A, and my denominator would be 4, because 4 and 6 are in corresponding positions. So this proportion would be true. 3 over 6 equals A over 4. It's not asking me to solve it or anything of that nature. Also, the flip-flop is true. The flip-flop would be true. So I know that 6 over 3 is equal to 4 over A. All I did here is use the larger side from E over the smaller side from E is equal to the larger side from F over the smaller side from F. And when I look over here, I do see the 6 over 3 and 4 over A. That's the first one. I know that would be a true statement. So let's go on and talk about how to set it up differently. Sometimes I use E and F in the same ratio. So for example, 4 and 6 are corresponding sides. I could write a proportion using the 6 over the 4. This is the longer side in E over the longer side in F. And it's going to be equal to another side in E over that corresponding side from F. So my other side in E is my side that's 3, and it corresponds to my side in F that's A. So this would also be a true proportion. And when I look over here, I see that this is actually my B. So the flip-flop of this is also true. I could write 4 over 6. That is the smaller side from, that's the longer side from F over the longer side from E. and that will be equal to, now since f is in the numerator, that would be a over 3, because the sides from e are in my denominator. So these proportions, all 4 of these proportions, are equivalent to each other. So take a look at the setup for C, D, E, and F, and see if any other proportions that they list there are also true for these pictures. By the way, if you solve any of these, if you cross multiply any of them, you're going to get the same answer for A. That's why they all work. So let me get a different color and just show you what I mean. Although they don't ask me to solve this, if I cross multiply, I get 6a equals 3 times 4, or 12. Divide both sides by 6, I get a equals 2. If I solve this one, I'd also get a equals 2. If I solve this one, I'd also get a equals 2. I'd also get a equals 2. That's what makes all of these a correct proportion for these 2 diagrams. So flipping it over, there are 3 more proportions that you have to do. I might tell you though, as you're doing them, if it doesn't divide evenly, sorry, I don't know why it gets blurry. If it doesn't divide evenly, go ahead and leave answer as a top-heavy fraction. But if you can reduce it, you need to reduce it. But if it's a top-heavy fraction, you're fine. Oh, leave answer, A and S. Okay. So then 4, 5, 6, and 7 are all review. I originally had the wrong assignment on Schoology. It's been corrected, but it's 1 through 7 all plus the proportions I'm going to give you. So let's write down those proportions so you have them. So after number 7, let's write down the following 3 problems. So number 8, I'd like it to be 2/3 equals x over 7. Number 9, I'd like it to be 3/5 equals 12 over x. And finally, 10, I'd like it to be 1/3 equals x over 45. Solve these for your homework as well. Thank you very much.